Hello everyone. So today we're going to continue on 9.3 surface integral. So if I remember correctly, our last video we get to talk about these two formulas right here on the screen. One of them is to calculate the surface area of some kind of surface in R3. So the problem here is that we have to be able to form a parameterization of the surface, and which allow us to actually use this integration to integrate to form the surface area. I also mentioned that this cross product, the length of this cross product du dv, is often referred to as a surface area differential. And so when you integrate surface area differential, you get the surface area. Now, one thing I do want to point out is that how is that different than area differential? So area differential is referred to when you have a planar object, a planar like enclosed region that's on R2. So a surface area differential allow us to find the surface of surface area of a surface that's in R3. So to show you the difference, if you look at like in this UV plane, if I do du dv, that would form a coordinate rectangle on the UV plane. And that is called area differential. But that would actually transform into a kind of parallelogram shape over here. And that parallelogram shape can actually be not flat, meaning this parallelogram that you form is not parallel to the xy plane, but instead it could be tilted up or down based on the vector dg dv or dg du. So that's form what we call surface area differential, because it's not completely flat and parallel to the xy plane or the UV plane for that matter. So that's the difference between the two. And so of course when you integrate the surface area differential, you get the surface area. And we also learned that if we have some kind of density of the surface, we can actually use an integral by simply multiply the surface area differential with the density and then integrate. That would give us the mass of the surface. So here imagine that you have a piece of metal that contour into different shapes, so there's not a flat. Then you can basically use this to calculate. So obviously when you do that, you are assuming that this surface have a uniform thickness. That's the reason why the surface area dictate the mass and not the volume that would dictate the mass, because you have a uniform thickness. So therefore, when you imagine calculating the density, it will be just the surface area times the uniform thickness times the density, which equal to mass. And so now what happened is the density would absorb the uniform thickness into it, so that now you only basically worry about the surface area with the density. So that's how that usually works out. So today what I want to do is hopefully I will have enough time to go through two examples with you, and if I have more time than that, I will probably talk about some the next thing I want to show you. So here's our first example. So what I'm going to do with our first example would be to try to calculate maybe a surface area. Okay, so here's example. We go let g of uv, g of uv to equal to uv u squared plus v squared, and over some kind of domain u squared plus v squared is less than or equal to a squared. Now, some of you might not recognize this function, but it is a function that we have used quite often already. This function actually, the surface, or this surface, is technically the same as z equal to x squared plus y squared with x squared plus y squared less than or equal to a squared. So what kind of surface this is? So I'm going to draw it out into a parametric representation. Oops. To show you. So here's my UV plane. Our domain is actually a circle of radius a. So here's my domain. I'm going to go and call that D. I'm going to just shade it in. Now, what does the function, what does the function g do? G would turn this into a G would turn it into this surface that some of you probably remember seeing back in chapter 5. So here's my x, y, z space, and my surface actually will be this. Okay, actually, you know what? I'm going to use red. Okay. And we call that the paraboloid because basically it's a parabola spinning around the z-axis. Normally the paraboloid would go on forever to positive infinity to the z-axis, but this one, because they have a fixed domain of a circle, so that circle actually would corresponding to the circle that you see at the top, which is x squared plus y squared equal to a. And then it would, as the circle becomes smaller, it kind of follow this parabola until we get to the tip, which is at the origin 0, 0, 0. So what we're going to try to do is try to find the surface area for that. Now, as a matter of fact, by now you should recognize that you could actually find the surface area for this using a surface of revolution. Just rotate around the z-axis, which is perfectly fine. But of course, here what I'm going to try to do is to show you using a using the surface area differential to do that. So let's go ahead and try to see if we can figure this out. So to do that, what I need to do is basically form this integral. And we'll call this surface S also. It's a double integral over D. dg over du cross dg over dv. Oops. The length of that, du dv. Now, I know I write down du dv, but remember, that does not mean that we have to integrate du dv, because not until we set up our limits, this is just a Riemann integral. So du dv here just simply represent the two differential that we're integrating, or sometimes referred to as the area differential. And remember, because this talk about integrating, even though it's finding the surface area, is integrating on the uv, meaning that it's integrating on the uv plane. So it's two-dimensional. So to do that, I guess I'm going to have to find dg over du, which should be pretty easy to do. dg over du should equal to 1, 0, 2u. And dg over dv would equal to 1, 0, 2v. So that's pretty symmetrical. And now what I'm going to do is simply form the cross product between them. So I do assume that you know how to do a cross product. So I'm not going to really go through how to find the cross product. But if you do that correctly, you should get negative 2u, negative 2v, 1. Okay, and if you don't remember how to find the cross product, go back to chapter 1 and look it up. It's something that you have learned already, something that you have mastered how to do. If you don't remember, you just have to look it up. I would not be able to reteach you everything that I taught you this year. Okay, so now then I can actually find the length of this cross product. And the length of this cross product, remember, kind of represent the area of a parallelogram that we use to kind of fit to form the surface area. Would actually equal to square root 4u squared plus 4v squared plus 1. So seem to me that would be what we are trying to integrate. So let's go ahead and set up our integral. So seem to me that our area differential, or our area integral, will be double integral over d of square root of 4u squared plus 4v squared plus 1 du dv. And that's actually a pretty difficult integral to do because of the u square and the v square. However, if I'm thinking about this correctly, we are integrating over a circle on the UV plane. And lucky for us, we learned something back in chapter 7.4, which is called change of variable, which allow us to actually use a different coordinate system that will allow me to set up my integral in a better way so that I can actually integrate it. So in this case, what I'm going to do is I'm going to actually use the polar coordinates to complete my integral, because this integral I would not be able to do. So polar coordinate transformation would tell me that I can now set up my integral to be the following. Because I'm going through the entire circle, I'm going to say theta from 0 to 2 pi. You know what? Actually, I'm going to integrate r first, because I have a feeling that r would have more of an actions going on. So I'm going to say r from 0 to a, and theta go from 0 to 2 pi. So that should give me the entire circle with radius a, and inside and to the boundary. So now the question comes down to what would happen to my integral. So if you remember in 7.4, once again, if you don't remember, you should look up your notes. I'm going to have to first change my integrand. So u would be kind of like x, so it would be r cosine theta square plus 4. Y would be, v would be like y, which is r sine theta square plus 1. And here's the important part to remember. Du dv would actually turn into r dr d theta. And remember, the r is what we call the Jacobian determinant. So don't forget, because we basically change the variable basically using Jacobian theorems. So if I'm looking at this correctly, notice the r cosine theta square and r sine theta square will just become r square cosine square theta plus r square sine square theta. And I can factor out the r square, and cosine square theta plus sine square theta become 1. So if you do this whole thing correctly, we should have this. And once again, if you just go through the math, you should see the exact same thing. Even if you don't follow, don't see immediately how this come out to be this, and I'm actually put the r in front, you should be able to do it yourself to figure it out. If you don't see what I did here, it doesn't stop you from doing it yourself and see if you get the same thing I do. That's how you learn. Okay, so if you don't see it, just try to do it. Try to expand everything out, square everything, and then see how you can combine them. And hopefully you get to where I am. So now this is actually manageable because I can actually integrate this using u substitution. And I know we start from a variable and then change to polar coordinate, and then now I have to use u substitution. So here I'm not going to use what we call u substitution because I actually u is already some kind of variable involved. So I'm going to call it w substitution. I'm going to let w equal to 4r squared plus 1. So dw would equal to 8r dr, which we have a r. So I'm going to go and move the 8 to the other side. So therefore, I'm going to go and actually do the integration so that I can just put the antiderivative up. So my integration of r square root of 4r squared plus 1 dr would actually become 1/8 integral of w to 1/2 power dw. And so that come out to be 1/8. The integral of w to the 1/2 power is 2/3 w to the 3/2. Normally I would put plus c, but here we are not doing an indefinite integral, so I'm going to forget about the plus c. And so this come out to be 1/12 4r square plus 1 to the 3 over 2 power. So therefore tell me that my integral is theta from 0 to 2 pi. And then this whole thing would integrate to 1 over 12 4r squared plus 1 to the 3 half, evaluated from r equal to 0 to r equal to a. And I still have the d theta that I have to deal with. So if I plug in 0, I actually don't get 0. So that's a little tricky. If I plug in 0, I actually get 1 to the 3 half power, which is 1. So times 112, which is 112. So therefore I have integral the theta from 0 to 2 pi. And if I plug in a, the whole expression kind of just stays the same. So 4a squared plus 1 to 3 over 2 minus 1 over 12 d theta. And notice that this whole thing does not involve theta at all. So I can actually just pull this whole thing out, because this whole thing is a constant. And just deal with the integral from 0 to 2 pi d theta, which would be just be theta divided from 2 pi minus 0, which is just 2 pi. So you know what? I'm just going to write the next line. So therefore, just be 1 over 12 4a squared plus 1 to the 3 half minus 1 over 12 multiplied by 2 pi. So therefore, become pi over 6 4a squared plus 1 to the 3 half minus 1. And that would be the area of this surface. Let's try that again. There you go. Much better. Oh, somehow the negative the part of the plus sign go away. So that would be our area. So notice it's not too bad to do, as long as you recognize that this requires you to do u substitute to do a change of variable, and then this requires you to do u substitution. None of these are new. You have learned all of these already. They all become part of the technique that you need to be able to use when you need it when you're doing an integration. So, hopefully I have time to finish my next example. So my next example will be calculating mass. So, problem will be very similar. So just with different function. And we're going to let, let's see how I word this here. Let g of it, okay, so I'm just going to define the parametric representation of the surface. I'm going to say let g of uv to be equal to u cosine v, u sine v, and v. And we're going to define u to go between 0 and a, and then v is going to go between 0 and 2 pi. So some of you may recognize this function also, u cosine v, u sine v, v, or if you probably remember just cosine v, sine v, v, and that would form a helix with a radius of 1 circling around the z-axis. Now in this particular case, our u can go from 0 to a. So therefore what we have is actually like, I don't know how to describe it. It's like, maybe I try to draw it. Actually, you know what? No. Now that I think about it, I don't think I would be able to draw it. So here, imagine that you have kind of like a spiral staircase. That's basically what it is. That go around one full circle. Yep, I think that's probably the best description I can give you. So if you don't know what a spiral staircase looks like, go look it up on Google, okay? So what we're going to try to do is the following. Let's say we define a mass. So let g of x be define a surface in R3, and we're going to call this surface S in R3. Let S have a density of mu of x, y, z is equal to x squared plus y squared. So meaning at any point on this surface, based on the position the density actually equal to just x squared plus y squared. So basically just the square of the distance from the z-axis. Notice it doesn't give you a z value, but x squared plus y squared will form kind of like a circle. Or if you think about it, it's like the square root of x squared plus y squared, which is the distance formula. So what I'm going to want to do is go ahead and try to find the mass of S. So the mass of S, I'm going to call it M of S, is basically given by this integral. So that's the domain, the density function of the parametric representation of the surface multiplied by the surface area differential. So it's literally kind of the same thing we just did, except that we now have to also multiply by the density function. And once again, I'm hoping that, you know, we will be able to integrate this. And if not, we can probably get through at least the first integration, then use a calculating device to do this. Okay, so let's go and try to get all these little pieces together. So since G is u cosine v, u sine v. So I'm going to go and say that dg over du would actually be cosine v sine v 0. And dg over dv should equal to negative u sine v, u cosine v1. So now let's go and do the cross product between them. So once again, I'm not going to go through the cross product. I'm assuming that you know how to do cross product. So the cross product come out to be sine v negative cosine v u. The last one is a little tricky because the last one actually come out to be u cosine square v plus u sine square v, which then cosine square v plus sine square v become 1, so therefore it becomes just u. And so in this case, the length of this cross product would just equal to square root sine square v plus cosine square v plus u square. So that come out to be just square root of 1 plus u square. Okay. Yes, notice that a lot of time you have run into cosine square plus cosine square v, or cosine square something plus sine square something, which turn out to be 1. It is a very powerful trick that you need to be able to use. Otherwise, you go find out that you get stuck a lot. So, you know, learn to use it. Now, here's the interesting thing also. If I look at the density function, so density of g of uv would basically just be x squared plus y squared. So therefore, it will be just u cosine v squared plus u sine v squared. Oh, you know what? I am sorry. I apologize. I meant to say that the density is the square root of that. So that would literally be just the distance from the z-axis. My mistake. So therefore, I'm going to put a square root of that also. So notice once again, that's become u squared cosine v squared plus u squared sine v squared. So that just become u squared. And under the square root, we just make it become u. Okay, fair enough. It should be plus or minus u, but remember it's a density, so we only allow positive value. So I would say this just equal to u, and our u is definitely a positive value because it goes from 0 to a. So I think we're all good. So now we have everything. So now I'm ready to go ahead and form my integral. So the mass of this surface S is equal to the integral over d of mu of g of uv, which is u, multiplied by the cross product length, which is 1 plus u squared under the square root, and then du dv. So it seems to me that that is the integral that we try to calculate. And we have our limits. So look like our integral region of integration defined by uv is just simply a rectangle, because it goes from u0 to a, and v go from 0 to 2 pi. So that's pretty straightforward. So what I'm going to do is I'm going to go and do this. I'm going to go and do just integrate uv, because it seems to me that u have a lot more actions going on also. So v go from 0 to 2 pi, u go from 0 to a, and I have u square root of 1 plus u square du dv. Now, once again, the integral of u radical 1 plus uv is u substitution. As a matter of fact, it is the exact same integration that we have done here, except that like the inside derivative is not 8r. Okay, so I'm going to assume that you should be able to do this integration. Okay, so if that's not the case, I would say you're really gonna have to do some studying on your own. So that should be 1/3 1 plus u squared to the 3/2, evaluated from 0 to a. So once again, be careful when you're plugging 0, it does not become 0. Oh, I forgot a dv, because it actually become 1 to the 3/2 power, which is 1 times 1/3. So therefore, this is integral v from 0 to 2 pi, 1/3 1 plus a squared to the 3/2 minus 1 dv. And just like with the last example, this whole thing have no v in it. So therefore, I'm going to go and pull this whole thing out of my integration and just simply integrate from 0 to 2 pi of dv. So that becomes just v, go from 2 pi to 0, which is just 2 pi. So therefore, my final answer should be 2 pi over 3, 1 plus a, 1 plus a squared to 3/2 power minus 1. And that gives the mass of this surface with the density function of radical x squared plus y squared. Alright, that looked like I make it just within 30 minutes. So I'm going to stop right here for this video, and we'll continue some more on our next video. Alright, talk to you guys then. Bye-bye.